Hello, everyone. My name is Carson Reed, and today we are talking about machine learning security and basically just seeing um, how models are exploitable or vulnerable to different ideas and how that could affect our organization. And so we'll be looking at three articles relating to ML security and yeah, just see what the implications are. So for the first article, we have AI/machine learning for network security. The emperor has no clothes. That's the article title. And so basically the main purpose and the main idea of this article was that models can be prone to underspecification. And so basically what underspecification means is that, the point of a model or like a machine learning network is to learn how something works, right? So you could have images that might have like a cat or a dog, and the model's supposed to be able to figure out, oh, if I see an image of a cat, it knows it's a cat. Now, these certain models, some are prone to underspecification, which means that it doesn't actually learn the innate features of what it means to be a cat or a dog. It just notices certain details that in its training data set, it kind of learns a shortcut, basically. Like, so say, for example, on the training data set between cats and dogs, all the cat photos had like a picture of a book in the top right corner or something. And so the model learned that, oh, an image of a cat is a cat because it's got that little book in the corner. Obviously, that's not actually learning what a cat is. And so if you were to throw a picture of a cat without one, even though it should be able to know that's a cat, it won't because it doesn't see that little icon in the corner. That's a basic version or a basic explanation of that. And so essentially the paper or the writers of the paper understand that it's hard for network operators to know when a model is underspecifying or if it's just or if it is or is not underspecifying their training data. And so this paper focuses on trying to help network ops figure that out. And so for a model to be effective, it needs to balance model fidelity, complexity, and stability. And so fidelity is referring to the accuracy of the decision tree. Complexity is the size of the decision tree. So obviously the bigger it is, the more complicated and more searching has to do. And then last, stability, which is concerned with correctness and coverage and all that. Now the paper references this trustee framework, which is supposed to help analyze these different things and then determine like if these decision trees have these inductive biases with the underspecifying. And so in their summary, they test different networks or different models on like Heartbleed vulnerability, VPN versus non-VPN traffic, IDS malicious traffic, all that stuff. And their results were all right in being able to determine if their models were underspecifying. And so that's kind of what the point of the article was. I would say strengths was that it was pretty thorough on the different explanations and like the examples of when a model looks good, is underspecifying XYZ, all that stuff. And so it made it really easy to follow and understand that. A weakness, though, is that they're just addressing the problem of a model underspecifying. They don't really come up with good solutions to how to fix your model if it is underspecifying. And so it would have been nice to see some more solution-based stuff from that. And so the relevance to our organization is we just need to make sure that we're doing these kind of checks with our models. And so even though we've trained data with our model and we've done testing and it looks good, we need to test it with other data in a slightly different environment, but with the same goal to see if our model is actually effective in learning the actual problem and not just this underlying pattern that doesn't really matter. So now we'll go to the next article, which is titled On the Security Risks of Auto ML. And so this paper was tackling the security problems with NAS, or Neural Architecture Search. And so what NAS is, it's a part of AutoML. And so basically what NAS does is it can search and help create models automatically, which is obviously really helpful and nice because if it automatically does it for you, you can pump out models really fast. As someone who's worked with some machine learning stuff with RF frequencies, it can be really annoying to tweak and tune parameters. And so having something like this is super nice. However, the article addresses and has found this problem that there's not a lot of security risks known about NAS in terms of the models it produces. And so after some experimentation, what they did is they took, I think it was 10 NAS models and compared it against 10 non-NAS models. And basically what they learned is that the NAS produced models tend to be more susceptible to a larger attack surface. And so the different attacks that they tried against both, obviously, both the NAS and the non-NAS, was model poisoning, backdoor injection, functionality stealing, and different member inference. And that last one we'll get to a little bit more in the next article. And so basically, after doing all those tests, they found that the NAS ones tend to be more vulnerable to these attack surfaces. And their hypothesis was that it's because when NAS was evaluating their models, if they were good or not, they would perform their evaluation before full convergence. And so obviously it doesn't seem that wise to perform an evaluation before you've completed, the entire convergence of your model. And so they think that's part of it, but also that they favor models with higher trainability. And so essentially models that converge early on during their training sequences, they will favor those and be biased towards those. And that leads to models with high loss smoothness and low gradient variance, which means that they don't cover a larger basis. And so the mitigations they thought to help prevent this would be post-NAS adversarial training. So even after it's created a model, you want to do some extra training to make sure it's not as vulnerable as your typical custom handmade model. And they also suggested to increase cell depth and suppress skip connects. And so the strengths and weaknesses with this article, a strength is that it does a good job of alerting the community that there are actually security risks incurred by NAS. And so that was the whole purpose of the article. So it did good on doing that, and it did well explaining and coming up with reasons as to why it could be doing that. A weakness is that the mitigations, the mitigations might have negative impact specifically on model poisoning, the cell depth and the skip connections, suppressing those. After testing with that, it seemed to do well against the other vulnerabilities I had mentioned, but specifically against model poisoning, it had a negative impact and it actually wasn't as good. And they also didn't consider other NAS frameworks. And so they thought as a further works was to try other versions of NAS and to kind of expand their testing through all of that. So how is this relevant to our organization? Basically, we just obviously need to be careful using NAS models and just making sure that the models that we choose aren't more vulnerable than something we can make ourselves. Obviously, with security is really important. And so if it takes a little more time to create a handmade model to prevent security issues, then we should definitely do that over a NAS model, because I think that time we spend is worth our money to not get attacked. So the last article we come to is this one titled ML Doctor Holistic Risk Assessment of Inference Attacks Against Machine Learning Models. And so the main purpose of this article was to create a more comprehensive picture of the risks caused by inference attacks and kind of help explain to the reader sort of what these attacks are, and then come up with this framework, ML Doctor, to help defend against this a little bit. So first of all, it's important to know what an inference attack actually is. And so it's an attack against a machine learning model that helps the attacker learn highly sensitive information about the model, the parameters, the training data, all that stuff. And so we have these different kinds of inference attacks. And so the first one is a membership inference, which is able to determine whether or not a target data sample was used to train a machine learning model. Excuse me. And so, for example, this would be a problem like if you did training data on drug dose predictions for patients, you could leak, a patient's health status from this kind of attack. And so that's a highly important piece of information. And so you don't want that to get out. The next one is model inversion. And so this attack aims to reconstruct data from samples from a target machine learning model. And so this would let an adversary learn directly information about training data. So kind of similar to the first one. And the example given in the paper was that a machine learning model that was made to record, facial data and learn facial data, an attacker could get the facial data of a victim with this attack, assuming that data was used to train a model. The third one is attribute inferencing. And so this one aims to exploit that models might learn extra information about training data that's not related to the original task. So for example, a model that might be used to predict age could also, in the meantime, like during its training, learn how to predict the race of an individual. And so attackers can exploit this to get more out of a model than is really supposed to, give you. And then the last one is model stealing. And so this one aims to extract parameters from a target model. And so an adversary is basically able to obtain a copy of the model that they're targeting. And this is a problem because, this is essentially property theft or intellectual property theft, because someone might spend a ton of time creating this model, and yet an attacker can just essentially copy it. And so with all of these things, obviously these are all big problems about learning information from a model. And so what the article did was try to create this ML doctor, which is supposed to provide analysis and defenses against this kind of attack. And so these defenses could be differential privacy, which guarantees a single data sample has limited impact on an output. That way it doesn't have, you can't pull data from, or you can't pull information from the sample data that has a huge impact on the model. It's across the board. All the training data comes together to help train the model, but not one sample has a ton of impact. And then you have knowledge distillation, which transfers the ability from a larger model to a smaller model, which is supposed to help it make more efficient and less dependent on resources, but they found that this defense wasn't actually that great. So strengths of this article, it did a good job showing the current, attack problem with these machine learning models, that you can extract information out of them. And that was, again, part of the point of the article, so they did well. A weakness is that this ML doctor thing mostly is for image classification and can help mitigate, inference attacks for those types of models. But for other types of models, like anything else, it's not as good. And so part of their future work is to be able to create ML doctor in a way that will be more effective for different kinds of models. And so the relevance to our organization, we just need to be aware that if we're not careful, our models can have some information extracted out of them. And so we just need to be aware, like, hey, if we have sensitive training data, we need to test this and make sure that attackers aren't able to extract that. So the overall cross-cutting theme to know is that machine learning models are vulnerable to attacks. You don't normally think of a model that's used to predict stuff to be exploitable, because it just seems like it's just a model, it just predicts stuff. But it's important to note that they are vulnerable to attacks. Number one, they have inherent flaws. Like we saw with the underspecification, a model just might not be very good at something when we think it is. So like if we had a model that underspecified an IDS, we might think that it's doing a good job detecting attacks, but it's not. And that's obviously a big security risk. The next one is they're hard to analyze for vulnerabilities. We're looking at that NAS article. Sometimes it's hard to tell whether or not something does have this large attack surface. And so we need to be aware of these automatic model creation tools, that they could be more vulnerable. And sometimes it's hard to figure that out. And then last, that models are tricked into revealing information. And so they are vulnerable to being tricked into ways of extracting information out that we don't want attackers to know. So basically, as an organization, we just need to make sure we are checking our models, making sure they are not susceptible, or at least less susceptible to these attacks, and just be vigilant when we are creating these or choosing models that are already out there. So hope that was interesting and helpful. And that's all I have. Thank you.